Thank you.
Okay, morning, good afternoon, good evening, depending on which time zone you are in and which country. This particular webcast, which is specially tailored for Palisade and at-risk, is titled Using At-Risk in Load and Resistance Factor Design, which we call LRFD, Approach in Civil Engineering. And this particular topic of LRFD has really become very interesting to a lot of people because it's now mandated in the United States by lead agencies such as the Federal Highway Administration and the American Association of State Highway and Transportation Officials. Now, there are a lot of civil engineering features which use LRFD, primarily bridges and retaining walls, and little known fact is that the pavement design procedures in the United States and in a lot of countries are also based on probabilistic based designs, which use similar principles as LRFD. Now, the AASHTO version of LRFD really started out in 1994. What I'm showing you in the table here are that we are in the 6th edition of AASHTO right now, which was just released about 5 or 6 months ago, and that's the 2012 edition. And each one of the edition had several interims in it. And the purpose of the interims were to probably correct errors or add more information as more data was collected and so on. And what you see in the picture here on the right-hand side is the cover page of the 2012 edition. Now, it really did not start getting into the design aspects till about 2004. And that was because the Federal Highway Administration mandated in the United States that if you need federal funding for your bridges and retaining walls, thou shalt use LRFD. So that was the impetus of starting the LRFD process in real-time application. Now the question comes up, what about this LRFD versus other practices? The acronym LRFD is used specifically by AASHTO and the transportation practice in the United States. Now there are practices worldwide, for example, Europe, Canada, Australia, Japan. In fact, various agencies in the United States itself, like Electrical Power Research Institute, which use nomenclature like limit state design or reliability-based design. Practically, they are the same principles. The concepts, the basic concepts are similar in the sense that they are based on probabilistic or what somebody might call stochastic approach. The thing to remember, though, is that the terminology may be different. The way things are calibrated in different codes might be different. For example, here in the United States, we deal with calibration at the model level, while in the Euro code, some of the calibration might be done at a parameter level. So there are different levels of uncertainty which need to be addressed. So what I would suggest is that when you listen to this presentation, I'm going to necessarily make it a little bit generic so it applies in the United States as well as elsewhere in the world. What I would alert you is that be careful about the definitions in your respective codes, and one big thing is do not mix the codes. So don't start mixing the Euro code with the AASHTO code and so on, because you will be mixing several different concepts and creating problems. Now, regardless of whether you are in Europe or Canada or Australia or wherever you are, the basic thing is that we want to make our structures safe. What is the basic expression of safety? Well, one might call it load less than the resistance. Somebody might say it's resistance greater than the load. Or some people might want to talk in terms of capacity and demand. So if you speak in those terms, then capacity is greater than demand or demand is less than capacity. And what we are going to do in this particular webcast is that we are going to use the words load and resistance, and we are going to use the first expression of safety, which is load less than resistance. Now, when you think about it, that expression of safety is also called a limit state, because if you violate that expression, then you are violating a certain limit which can create a problem for you. Okay, so what I've written in the bottom box is load less than resistance is a limit state, which if violated may lead to undesirable consequences. Now, what is undesirable consequences? Well, that would depend on the owner on what they consider to be undesirable. So we'll take a look at all of those kind of aspects as we go on in the webinar. Now that we know that the expression of safety is also called limit state, and that's load less than the resistance, let's designate load by Q and resistance by R. You see that red symbol in there, less than? My question is, what does that mean? And you might be thinking, why is this fellow asking me that less than is not greater than or equal to? But what is really the meaning of less than or greater than or things like that in these kind of expressions? Well, here is the key thing. The meaning of less than is as follows. It means that load is less than the resistance after all the uncertainties in the load and resistance have been accounted for. So which means on both sides of the expression of the less than sign there, you have incorporated your uncertainty. And of course, what would happen is that if you want to incorporate the uncertainty, then to characterize the limit state, you must need a definition of uncertain events and uncertainty itself. So the question now comes in is that, okay, how do I express uncertainty? And there are two ways to do it. One is deterministic, and the other one is probabilistic. The first one, the deterministic, is often subjective, where people say, oh, I feel it's safe. Or if your structure has this much more resistance than the load, or what we call a factor of safety, then it's called a deterministic approach. While the other approach, the probabilistic or the stochastic approach, is based on an assessment of risk. So let's take an example. For everybody has driven on roads. Probably the way you came to your office today was driving a car or things like that, and you were on a certain roadway where there was a certain speed limit sign. Well, what's the purpose of that speed limit sign? The limit state for that one is that your actual speed should be less than the speed limit. What are the uncertainties in all of these things? Well, the uncertainties might be the traffic count or data, the amount of traffic you have on the road. Even if you wanted to speed and it was bumper-to-bumper traffic, you could not have speeded. Or if you have an empty road, then your temptation is to speed. It would also depend on the vehicle type and distribution, the traffic models which were used, others and things like that. But it's very interesting. I mean, a stark reminder of a limit state every day is this fellow on the road in that car with flashing lights. If you are going to exceed the speed limit, then you're going to pay the consequence, and that is an undesirable consequence. So you see on how we can apply the concept of load and resistance factor design, which is also known as limit state, to commonplace applications. And now this was for roadway. Let me take another example. This is a project which we had in Tucson where a wall just blew out on us. It was on a hillside, and what you are seeing is the portion of the retaining wall just fell out on us. Now what's the limit state in this one here? Well, the limit state is that if the load was less than the geotechnical resistance. Now geotechnical is for people like me who deal with the soils and foundations and things like that, and if the resistance of that soil or foundation happen to be less than the load, then you have a problem. So our desirable limit state is to keep load less than the geotechnical resistance, and the structure should be safe. So what are the uncertainties in this one? Well, it might be the property measurement. How did you measure the load, or how did you measure the geotechnical properties? And once you define the geotechnical properties, what was the variability in those soil properties? What kind of model you used? And there can be a host of other ones there. When I keep on saying others, well, let's talk about other examples of limit states, okay? And now you can really start talking about limit state in your everyday life, showing up on time. For example, if your appointment somewhere is at 8 o'clock in the morning and you showed up a couple of minutes late, well, is that a limit state which you violated? Yes, you did. What were the undesirable consequences there? Well, that depends on what you were late for, okay? Population growth, for example, if there's a new town being planned and they planned for 10 million people population in there and started developing the infrastructure resources for only for 10 million, and then the population just grew on, and then there was an influx of population and it became 12 million. Well, what happened to your resources? That's a problem there. Occurrence of crack in a structure. Look around your building wherever you're sitting. Do you see a crack in a structure? Is that a limit state? Coastal storms, games. You can play games and you can have problems there. Conflicts, wars and things like that, you can use load and resistance factor design. There are many others. I mean, in fact, your imagination is your limit, and if you take a limit state based on your imagination, then consider this thing. The reality might be the resistance while imagination is the load, right? So what happens in all of these things is that you can use any consistent quantities on both sides of the inequality and express the limit state. Now when you do that, you need to incorporate the uncertainty on both sides of the equation or both sides of the inequality. Now, what uncertainties? There can be many uncertainties. I'll take some of the most mundane or the esoteric ones. For example, aesthetics. I built a beautiful bridge like this. This is the San Francisco Bay Bridge. Okay, I took a picture of that from the coast there. It looks beautiful to me, but to somebody else, it might not look good. That's an uncertainty. When we are in the hurricane season, look at those 3 hurricanes stacked one on top of the other, ready to hit the Louisiana coast. Or look at the next one here. Look at that storm covering the entire United States. This happened to be in February of 2011. So you can have coastal storms, you can have superstorms. We are in an election season here in the United States. How will the whole thing turn out? There's uncertainty on both sides of the political parties. You can have others. You might have construction, bidding, human error, a bunch of different ones there. So the question now comes in, all right, I got a lot of uncertainty. Let's first of all try to categorize it. When I try to categorize it, I might say it is a natural uncertainty or it's a knowledge uncertainty. Now in terms of the natural uncertainty, it might be values which change with time. So we call it temporal. There might be values which change based on location. We call it spatial. So there are different kind of uncertainties there, but to all of those uncertainties, we are going to be applying a model to show our knowledge of the uncertainty, and each model is going to have certain parameters which by themselves will have uncertainty. So how do we characterize all of these things quantitatively? Where do uncertainties apply? Well, all of us agree that it applies to all aspects of design, regardless of the structure, type, size, or location. Whether I'm sitting here or I'm in Argentina or in Australia or things like that, well, the uncertainties still stay there. In fact, they affect all design features. So what should we do? Well, we need to try to quantify uncertainty. So what we are going to do is that we are going to try to collect the data and study the spread of the data. How do we do that? Let me take a very simple example. I got a concrete cylinder here. I've shown a cylindrical shape. Let's assume it's a concrete cylinder and that I'm going to put a load on top of it. When I put a load on top of it, I get what I call unconfined compressive strength of a cylinder in pounds per square inch. And let's say I'm going to do a number of tests which is shown on the x-axis. And let's say I did 28 tests. And I got a bunch of different values of the unconfined compression strength. The maximum value was 3600 psi, the minimum value was 2300 psi, and if I take an average of all of these things, the mean value, then that's 3100 psi. Well, that's nice. I mean, I see all of the data spread around the mean. Is there a way that I can capture that data spread? Well, what we can do is that we can say the mean is the peak value and the data spreads around from it, and as you go away from the mean value on either side, the chances of you having a data point lying towards the tail end of it starts to become remote. Not zero, but a small amount there. So this kind of a curve, we can now start looking at it, and it's called a probability distribution function or probability density function or whatever you want to call it there. But it looks like a bell, right? So oftentimes it's called a bell curve when it's a normal distribution. So this particular curve was for a certain max, minimum, and mean value for the data set which I showed you earlier. What happens if I add more data points to it? If I add more data points to it, then what would be the shape of this curve? The shape of the curve would be sharper, taller, because now we are less uncertain since we have more data. So you see, it all comes down to how much data you have and how you are going to be fitting a probability density function or probability distribution function to characterize the uncertainty. Okay. So let me repeat again. The mean value is the most probable value, and there is a chance that that value might not occur, and that particular chance is described by the shape of the probability distribution function around the mean. All right. So when we look at the probability distribution function, then when we are trying to address that, what is my probability that a limit state might be exceeded? What's the probability of something happening? Well, that's where we have to look at the area under the curve, because the probability of 1, or some people call it 100%, is actually the area under the probability distribution function. Okay, so if I look at this bell curve or the normal curve, you will see a nice bell-shaped curve, and you will see what we call M is the mean value right at the center where there's a peak value there. S is the standard deviation, and of course we can use coefficient of variation, which is standard deviation divided by mean. And coefficient of variation oftentimes is a better method to characterize the spread in the data, because you're often dealing with several different data sets, and the data sets might have quite a few different mean values and standard deviation values. So basically, to compare variables across different data sets, it's useful to have coefficient of variation, but that's your choice. Now you see what I'm calling it here. I'm calling it a two-tailed representation, because I got a tail on one side and a tail on the other side. Now depending on how far I go from the mean, either to the left side or the right side. For example, if I go 1 standard deviation on each side of it, then I see that about 68% of the data is contained within that particular zone. If I go 2 standard deviations on each side, then I'm including about 95.5%. If I go 3 standard deviation on each side, then it's 99.73. And of course, you can go 4 standard deviation, 5 standard deviation, and so on there. But practically after 3 standard deviation, about 0.1% or less than 0.1% is left at the tail end of those curves there. Now, that is the area under the bell-shaped curve. For our LRFD kind of analysis, the two-tailed representation is often not useful. We need to convert it into what I call a one-tailed representation. What do you mean by one-tailed representation? Well, in one-tailed representation, what I'm doing is that I'm just counting the area under one of the tails by describing the problem as follows. I would say, tell me the area under the curve which is a certain number of standard deviations from the mean. And this beta value which I put in there is the number of standard deviations. So you see now I plotted this mean line here to be completely in sync with the mean line above at the top. So if I'm moving to the left hand side to say 1 standard deviation, then I got 34.1% of the area under that curve there, plus 34.1% from the other side, 13.6 from the other side, 2.1, and so on. So the area of this green zone can be dictated by the number of standard deviations you have on the one side of the mean. Where can I get these kind of values? Okay, well, if you go to any standard probability or textbook there, or even in statistics textbook, you will find tables like this. All right, and what I've gone to is one of the books there and just taken few typical values, and this is a partial table here, and I've taken a few typical values. And let's say if I'm going 3 standard deviations, which is an x value of 3, then what I'll find out that the area under the greenish portion of the curve is 99.865%. Now I can start reading the table as follows. I can say that, okay, if I want 99.9% of the data covered, then what is that x value, which in turn means what is the number of standard deviations that I have to go from the mean there? That turns out to be 3.09. You see on how I read the table? Now you might say I want 99.98% of the data covered. Well, what's that value? How far do I need to go from the mean? Well, that's 3.54. Now, I'm explaining these things to you in the basic concept of what's shown in the statistics and the probability textbooks there. I'm going to be using the same concept in terms of what I call reliability index later on. So what I'm showing to you is that the things which are already available in the literature, how we will be using it in the load and resistance factor design concept. All right. So now, coming back to this slide again, what does the less than mean? Well, Q less than R means that we need to account for uncertainty on the load side, uncertainty on the resistance side. So I can have a probability distribution function on the load side. I can have a probability distribution function on the resistance side. Okay. Where do those distribution functions come from? Well, let's look at it as follows. We'll come to that in a minute, and at risk gives us an opportunity to have a number of different distribution functions. But before that, let's study this concept of safety once more so everybody understands on how we are going to use it. We know that the load has to be less than the resistance, right? That's the limit state. So if on the x-axis I'm plotting load and resistance, then by that definition, the load has to be on the left-hand side of the resistance, correct? Because only then it would be load less than resistance. And what I'm plotting here is the mean value of the load and resistance. The distance between the two, the resistance minus load, one can think about it as a safety margin. Okay, more the distance, the safer the design feature. Or you might take the ratio of the two and call it the factor of safety. The resistance divided by the load, the mean values, and as long as that value is greater than 1, then the structure is safe. Well, the safety margin and the factor of safety are what we call the deterministic expressions of safety. Why? Because nowhere in this definition have we accounted for the spread of the data around the mean. We simply use the mean values to get an idea about safety. That's what deterministic thing is all about. But now, do you think a factor of safety greater than 1 means that the structure is absolutely safe? Or a safety margin greater than 0 means the structure is safe? Well, we are in for a rude shock now. How is that going to happen? Well, let me now plot the spread of the data. This might be the spread of the data for the load. And look at the tail end of it. It goes quite far. Now I got the spread of the data from the resistance. That's nice, but they're overlapping. What is going on here? Well, in that overlap zone, I either have load greater than the resistance or resistance less than the load. Either way, it's trouble for me. It's a danger zone. In that particular red zone or the shaded zone, which I just did here, there is a probability that failure can occur. So you see, my friends, what seemed safe from a deterministic viewpoint still has a probability of failure. And our job is to figure out what that probability of failure is, and that is the essence of LRFD, or if you want to call it limit state design, or if you want to call it reliability based design, or stochastic method, or whatever you want to call it. So we are going to study that. So now when I look at it, I put a small inset of that figure which you saw on the previous slide there, and we learned that even if there is a safety margin, there is still a probability of failure. And now our job is to control the size of that red overlap zone by ensuring a certain safety margin for a certain probability of failure. When I say failure, what does that mean? It can mean a lot of different things to different people. Basically, what I think of failure is a certain adverse event where the event is defined by the owner who's trying to understand the problem. Okay. So now when I take a look at it, the problem now reduces to as follows. I need to control this red zone or the what I will call the danger zone or the overlap zone. How do I do that? Well, that's where I need to get into risk and reliability. Let's understand what risk and reliability mean. They're actually complementary terms. They do not mean the same thing. In fact, they mean exactly the opposite. Risk is associated with probability of failure. Reliability is associated with probability of success. Since the total probability is 1 or 100%, then one can say that the probability of success is equal to 1 minus probability of failure. A very basic definition, but that's where we need to understand that when we talk in terms of success, we are talking about reliability. When we talk in terms of failure, we are talking about risk. Okay? Keep that in mind. Now, let's talk in terms of numbers, okay, just to make sure I hit home the point here, risk or reliability. I say probability of failure is 10%. What does that mean? When people say there's a 10% risk, they're actually saying that the probability of failure is 10% or there's a 1 in 10 chance of failure. There's a better way to talk about it. You might say probability of success is 90%. where you might say, hey, the car which you are buying from me is 90% reliable. Well, that sounds better than saying there's a 10% chance of failure, right? So that's one way of talking about. So it's reliable. So now, reliable obviously sounds better than risk. Why does it do that? Because the word failure itself has a negative connotation, and we need to characterize that. So what we are going to do is, rather than talk in terms of the failure, we are going to introduce a new concept which is called the concept of reliability index. Now, when I talk about reliability index, by necessity, I'll have to talk about the probability of failure, but the essence of all of these design procedures, the LRFD, the limit state design, the reliability-based design, is all to characterize a reliability index. And let's see on how that can be done. Okay, I bring up this figure again, which you have seen before. The red overlap zone is what we are trying to control. That red overlap zone, listen to me carefully, it is basically an eye candy. Looks sweet to your eyes there, but it's just conceptual. We need to make sure that we can characterize the area of that overlap. You remember that area under the bell curve and things like that, where we went to the two tails and then I converted it to one tail representation? Well, forget about two tails. I've got four tails here. Two tails each for the load and resistance. And now two of those tails are overlapping. I have really made my life miserable here, correct? Well, I need to get a way out of this one here, because I need to measure that overlap zone. And how am I going to do that? I need a quantitative measure, and this is how I'm going to do that. This is where the concept of reliability index comes in, and everything which I taught you before. Everything which I'm discussing here, if you're interested in the commentary of it, just go and download this paper, which is on a website, which I'll give you later on. But take a look at this inset figure which I gave you. What I'm going to do, I'm going to write a limit state. And instead of saying the resistance is greater than the load or load is less than the resistance, I'm going to say that I'm going to take these two probability distribution functions, and I'm going to deduct the probability distribution function of load from that of the resistance. Okay. Once I do that, I get a one-tail representation. You see that? Now I've combined two probability distribution functions into one. And magically, I get everything into one-tail distribution, and all the concepts which I told you before fall into place. Look at that red zone there. You remember that red zone? I can figure out that red zone in terms of the number of standard deviations distance from the mean. You remember that? So now this red zone, which was the danger zone, I can actually convert it into a one-tail representation, and since it's a one-tail representation, I can figure out the area of that failure zone, and that area of the failure zone is the probability of failure. That's why anything to the left of the vertical axis is called a failure zone. Anything to the right side of the vertical axis is called the safety zone or the reliability zone. To put it in context again with respect to what I taught you before, we can make the statement that as the beta value increases, which means that this curve is getting pushed more and more to the right-hand side, which means that the area of the red zone becomes smaller and smaller. So do we all agree that as the beta value increases, the probability of failure decreases? Yes, it does. And that particular beta value now, we are going to call it a reliability index. So you see, we don't want to talk in terms of failure. We want to talk in terms of how reliable the structure is. So we are going to be talking in terms of the number of standard deviations from the mean value. That is beta. That's the reliability index. Now, again, to close the circuit on this one here, what is the mathematical relationship between beta and the probability of failure or the probability of success? Well, I told you that the probability of success is equal to 1 minus probability of failure. So you can choose to express it whichever way you want, but basically it comes down to measuring the area of the curve to the left-hand side or the right-hand side of the vertical axis. If you measure the area of the curve to the left-hand side, it's the probability of failure. If you measure the area of success, area of the curve on the right-hand side, it's the probability of success there. Again, to remind you of this one here. This is where the table from statistics and probability books comes in important. You see now, we are interested in the one-tailed representation. These things were given in the books. Microsoft Excel has a neat little formula where it defines the probability of failure. Now, the beauty of the at-risk program is that it is indexed to Microsoft Excel. So anything which you have in Microsoft Excel is available to you in at-risk, because at-risk is an add-in to the Microsoft Excel. So now we have got two very powerful programs working together at our fingertips, and really we can work magic on this one here, and I'm going to show you all of those things. So let me do one thing. I've taken this whole table, went into this formula, and plotted this curve for us so that we can see what is it that these numbers mean. What I'm plotting here is reliability axis on the index on the x-axis and the probability of failure on the y-axis. On the right-hand y-axis, I'm expressing it in 1 in 1 probability of failure, 1 in 10, which is equal to 0.1 here and things like that. And I simply went to Excel and plotted this function. Now take a look at it. What does a reliability index of 1 mean? Does it mean that there is no failure? And if there's a failure, how much is it? Well, a reliability index of 1 still means that you've got 1 in 8 chance of failure. Okay? What does 1 in 100 or 1 in 1000 mean? Well, 1 in 100 or 1 in 1000 means that you've got a reliability index of 2.33 or 3.1 or something like that. Now you can come and say, oh, what is 1 in 5000? It's about 3.5. Now you can come and say, that's interesting. So if the probability of failure keeps on reducing, then I wonder what the probability of failure is for a reliability index of 4. So let's go down, pick it up. It's about 1 in 10, 20, 30, 1 in 30,000. So now you start looking at all of these things and you say, I wonder how designs are done for civil engineering features. Well, civil engineering features are generally in the zone, shaded zone, which I just turned on. It's between 1 in 100 to 1 in 5,000, depending on what element of the civil engineering infrastructure you're designing. Now, that's for civil engineering. What about for who plays in the upper right-hand corner of this particular slide here in the zone of reliability index of 5.5 or 6? Well, that's where our friends from the nuclear power plants and all of those high-risk kind of facilities work in. So they work in the zone of 1 in 100 million or things like that, but obviously those structures get to be costly. Okay, so that is how you read all of these things. To put it in context again, all of this probability of success, failure, and the reliability index, I put together a very simple table here. Success on the left-hand side column and probability on the 3 columns here where I express it in percentage or 1 in X. So 90% success is 10% failure, or it's 1 in 10. If I want to express it in terms of reliability index, what does it mean? 1 in 10 means it's a reliability index of 1.3. 99% success is 2.3 reliability index. 99.9 is 3.1, 99.99 is 3.7, 99.999 is 4.3, and 99.9999 is 4.7. It is a non-linear relationship. That's what I showed you in the graph before. And our task is how to figure out to use at-risk to quantify all of these things. Before I go there, I want to show you something. The question of the reliability index and which area of infrastructure which we are working in. There's a very nice chart by Professor Baker from University of Maryland, and it's from one of his 1987 publication, and there are updated charts like this in his book by Baker and Christian also. But this one suffices for our discussion here. It's very interesting. On the left-hand side, I've got the probability of failure. On the right-hand side, I've got the corresponding reliability index. And then as you go on the x-axis, there obviously you go to the right-hand side, it starts becoming more and more critical there. And what I've shown you are the marginally accepted and the accepted lines in there. This is called the FN kind of a chart where people use to evaluate risk. So if you are dealing with commercial aviation, then that's a huge problem if a plane goes down. I mean, so you are dealing with in the range of 4.5 to 4.7 reliability index. if you're dealing with dams, then you might be in the 3.5 to 4.2 kind of a range and things like that. Nuclear power plants may be off the chart, or when we send a space shuttle up there by NASA, that might be off the chart there. You don't want even a probability of failure or reliability index of 4.7. You want 5.5 or 6. So where does our foundations fall in? Look at what I highlighted there. The foundations which we are designing for civil engineering structures, or what AASHTO says it wants for load and resistance factor design of 1 in 5,000. So that creates a place for us in terms of what we are trying to design with respect to other facilities. But again, you see the point I'm trying to make? This particular presentation, I've indexed it to civil engineering features, but you can literally apply it to any industry which you want. Okay, that's the power of all of this presentation. So coming back to civil engineering features, what AASHTO has said is that the probability of failure which we want for superstructures and substructures is 1 in 5,000, of our foundations is 1 in 100 to 1 in 1,000, exactly what I showed you in the previous slide. What it means that our playground for reliability index is 3.54 for superstructures and about 2.33 to 3.09 for foundations. All right, that's good. Now we know what we are dealing with. Remember, I told you early on that you have to define uncertainties and figure out what you are working towards. Now that I got my marching orders, I know what I'm working towards. I'm working towards a reliability index ranging from 2.33 to 3.09 to 3.54. That's my play field, okay? And how am I going to do that? How am I going to achieve that desired level of reliability? Well, I'm going to go from the qualitative overlap zone to a quantitative overlap zone, which is the area of the curve to the left-hand side of the vertical axis. And basically, here is what I'm going to do, okay? Take a look at this particular figure again, and you're seeing that quite often. You see the distance between the mean load and the mean resistance. Now pay attention to me, okay? When you see the distance between the two, here is what I'm going to do to control this red overlap zone. I'm going to take the mean value of the load and multiply it by a certain factor, gamma. Okay, I'm going to increase my load. Why am I going to increase my load? Because I'm uncertain about that load, and because I'm uncertain, it would be prudent for me to use a larger value of the load than what I've computed. So gamma is a load factor which accounts for uncertainty in the load side. What about resistance? If you've got a certain resistance, and if you're uncertain, what are you going to do? Increase or decrease the resistance? Well, this is resistance. If I'm uncertain, then I'm going to play it safe, and I'm going to decrease the resistance. So I'm going to multiply it by a factor called phi, which is I'm going to be calling it a resistance factor. Okay. Now, by control, what I figured out is that my load factor gamma is always going to be greater than 1 because I'm increasing the loads. My resistance factor is always, most of the time, going to be less than 1 because I'm going to reduce the resistance. So really what has happened is that by controlling the value of gamma and phi, by studying the uncertainties, I can, in a sense, control this red overlap zone. Think about it. If I put in a very large value of gamma and a very small value of phi, then I'm pushing apart these curves. If I push apart the curves there, then my red zone decreases and my probability of failure decreases. Now, what I'm explaining to you is conceptually that there is a whole host of different theories behind it which take into account the bias factor and things like that. For this presentation, it's outside the scope of the presentation, but I'm going to give you certain good references which you can read upon if you're interested in those. But for the purpose right now, we have got a load factor which expresses the uncertainty in load. This is the load factor on the left-hand side of the equation, and then I got the resistance factor on the right-hand side of the equation. And basically what we are going to come and say, instead of load less than resistance, I'm going to call it factored load less than factored resistance. and that factoring takes into account the uncertainty in each side of the equation on each side of the inequality. So basically, here is the summary. Load factor accounts for uncertainties in load, resistance factor accounts for uncertainties in resistance, and we need to calibrate the load and the resistance factor to achieve a certain desired level of safety no matter what you are trying to do in life. Okay. All right. How do we do that? There are different calibration processes. You can have closed form solutions, graphical solutions, you can have numerical solutions, you can do Monte Carlo simulations. There are some good references here by Haldar and Mahadevan and Novak and Collins for civil engineering facilities. And of course, when you go to the at-risk software, the power of the at-risk software is that it can allow you to do Monte Carlo simulation, Latin hypercube simulations, and you can calibrate the load and resistance factors in LRFD. How are we going to do that? So I'm going to shift my focus onto at-risk now, okay, now that we understand the concept. In at-risk, you have a number of different probability density functions, PDFs. In fact, I'm showing you only a part of those things here. If you go into version 6 of it, there are many more, okay. Now, when I look at it, more is not always better, right? It's almost going to a restaurant and you got a huge menu and now you have to make a decision. Well, yeah, we got to make a decision out of this one here to use something for load and resistance, but let's see if we can come up with something rational. All of these distributions, I know that there's uncertainty on the load side, uncertainty on the resistance side. So I can describe the uncertainty on the load side by any one of these distributions, and also on the resistance side, I can have any one of these distributions. That is the power of at-risk. Let me tell you why. Because if you were to go to do this thing by closed form solution or by hand, do you realize the equation for a Weibull distribution or a Pareto distribution or a beta general and things like that, it's not easy as it is for a triangular distribution or it is for a log normal distribution or a normal. It becomes very difficult. So the beauty is that once you have this at-risk program, you can then come in and select the distribution, and it has already got the equations programmed in there. Now, what do we do in civil engineering? Well, oftentimes for loads, we use the normal distribution. For resistances, we use the log normal distribution. I am a fan of using the beta or the beta general because I don't believe in open tails in civil engineering. Okay, if a load is 100 kips or 100 pounds, well, is there a chance that the load can be 0 pounds? No, it probably is somewhere between 80 and 120 or things like that. So there are finite ends there. So that's the beta distribution. But the fact of the matter is that oftentimes people use normal distribution and things like that. So we will stay with that, or log normal distribution. So let's stay with that in this particular presentation. So what I'm going to do now is I'm going to switch gears and go away from PowerPoint into my Excel spreadsheet to demonstrate to you on how at-risk is used. And before I go there, let me tell you, I pre-programmed a spreadsheet to set up a simple model, okay? And for simplification, what I've done is that I set up a model in which I had certain standard deviations and means and things like that. So I've identified the uncertainties and the type of the distributions. And then just for your sake, just when you start running your own things there and you say that, oh, on this fellow's computer when he was lecturing, it seemed to run fast or slow or things like that, or what version of Excel he was using, I just put in there the system I'm using there along with Microsoft Excel 2010. Okay. So now what I'm going to do is I'm going to go away from here and I'm going to go into the spreadsheet which I'd already set up. Okay. And this is it, the whole spreadsheet. And what I've shown you on the right hand side here, you see this figure here which I'm moving around. That is that your double hump curve, the load and the resistance, the four-tail version of it, and then I convert it into a single-tail version of it and things like that. So now what I'm going to do is that I'm going to start zooming in on this spreadsheet so you get a feel for what's going on there, okay? what I did was I said the description of the case. I mean, it happens to be Palisade webcast demo today. It's a case number of demo and things like that. And just for reference, what I've done here on this side here, I just put in the commonly used reliability index values. So for example, if it is a 1-in-1 failure there, then my reliability index is 0. If it is a reliability index of 1, then it's about 1-in-6 or 1-in-8 or things like that, and so on. I put together the significant range of reliability index for my purpose. I mean, I'm not in the nuclear power plant industry, so I haven't really gone to 5.5. I limited myself to 4.27 or 1 in 100,000. All right. Let's say I'm designing a bridge. A bridge weighs a certain amount, so I'll call that the dead load. There will be traffic on the bridge, so I'll call it the live load, okay? And then there can be different loads in there. It can be the wearing surface on the bridge, like the pavement surface on the bridge, or it might be a post-tension bridge and so on. And the fact of the matter is that the bridge needs to have certain resistance for it to stand up. For simplification, I'm not going to consider the wearing surface and post-tension. All I'm trying to tell you is that you can have any number of loads in at risk and you can add them together. For simplification, I'm just going to use the dead load and the live load. For the dead load, I got a mean value of 3.15, a standard deviation of 0.315, which is a coefficient of variation of 10% or 0.1. I've got the live load parameters, and I got similar parameters for resistance. And as I told you, for loads, I'm going to use normal distribution. For resistance, I'll use the log normal distribution. All right, so what am I going to do? Since I have all of these statistics here, I'm going to now assign it a certain risk function. So look at it. When I clicked on this particular cell, and I'll highlight for you 3.15, look in the formula bar here. What I've done is that I've built in a normal function for which the mean value is from cell G10 and the standard deviation is from G11. Well, where is G10 and G11? See, G10, that is the mean value, and this is the standard deviation. So you see, I built in that function. I did the same thing for live load, okay, which I'm highlighting now in the second yellow there. I did the same thing for resistance, but in this particular case, the resistance is a log normal distribution function like what I'm showing in the formula bar up there, where my cursor is moving. Now, you see, you want to see on how this distribution functions look. So you would go into this risk and say, I want to see on what is it it's actually sampling. So I go in here and look at it and say, this is interesting. The dead load is showing up like a normal distribution. Okay. Now let me go to the live load. Okay. I go to the live load and it's also showing it as a normal distribution. Now I can click and go into the resistance, and resistance is clearly showing a log normal distribution. You see, so you can study what kind of distributions you have put in there, and of course you can go into the model window and things like that, but I generally like to work from here, and let me tell you what the model window is. I mean, you can go into the model window here, and it will show you all of these different distributions which you have done in actually a nice distribution pattern, but I generally tend to look at the histograms because it gives me a good idea about whether the number of bins in the histogram is tight enough or good number, and I can adjust that. All right. Now here is what I'm going to do. I got this dead load and the live load, and I'm going to add the two, okay, and see what that distribution is. So you see, if I add up the mean values of the two, 3.15 plus 1.15 is 4.3, right? That's the mean value. So when I added the two, what kind of distribution did I get? Well, since I'm adding two normal distributions, it should be pretty much a normal distribution. So let's go and take a look at it. Here is the distribution, and it looks pretty much a normal distribution. And if you really want to figure out whether it's normal or not, you can go and fit a distribution and say, I'm going to fit distributions here. And it went in there, and you see what came out at the top. The normal distribution function came out to be the best fit. And that's what this red line is showing in there. So that's a normal distribution. Now you can come and say, show me on how the Y-bull looks like. That's the green curve. That would be the Y-bull distribution. What would happen if you got a logistic distribution, Laplace distribution, exponential distribution? Well, obviously the Laplace is not a good fit, right? I mean, you can go into a Levi distribution and you say, whoa, no, that's not a good case. So let me turn these things off. And let me go back to my normal distribution. That's a good fit. I'm satisfied by it. Now let's do something interesting. This was the addition of the two loads. Is there any way to figure out on how they were added? Yes. Take a look at this one here, okay? And I'm going to make this thing wider so you can see what's going to come your way. I'm going to use the overlay functions in here, and on top of that one, I'm going to overlay the distribution due to dead load and overlay the distribution to the live load. I just clicked on those two cells there, and let's see what happens. I'm going to take this first simulation and look at this one here. It's a nice graphical distribution where if you look at it, this green curve here, look at what about the mean value is. The mean value is about 1.1 or things like that, and that was the mean value for the live load. So this green distribution is for the live load. The blue distribution, the second distribution, is for the dead load, and the summation of the two, you get the total load distribution. You can graphically see what's going on. Okay, now on top of this, I can come and say, okay, I got this load in here, things like that. Let me clear the overlays. I got this load. Now I want to see if I plot the resistance on it, on what would happen. So I come here and I'm going to plot the resistance here. Okay, let's see what it looks like again for the first simulation. And look at it. What do we have here? Isn't that nice? I got this load curve and a distribution curve exactly like what I was teaching you. See that here? Load, distribution. I can actually go and zoom in on it, and you can see the overlap between the two in terms of the histogram. I'll show you smooth curves in a minute there, but now you see that they are overlapping and how much they overlap. All right, well, let's go away from here now. Let's zoom out of it, and let me minimize this one. And now here is something I'm going to do. I'm going to leave this one on here, and we are going to do something interesting. We are going to actually run a calibration. And what my goal is that I want to run this calibration and see whether it meets my expectations. My expectations are as follows. I want a probability of failure of somewhere in around 1 in 700. So look at that table up at the top. 1 in 700 is about a reliability index of 3. Because I said that, you know what, it's a civil engineering feature, and I know the normal range is 1 in 100 to 1 in 1000. So let me aim for 1 in 500 to 1 in 1000, or an approximate reliability index of 3. Okay, so that's my target reliability index, and I said I can live with a range of plus or minus 0.1, because look at it as follows. Look, my friends, if you say you want an exact value, you are dreaming. Okay, because there's always uncertainty and you cannot be perfect. So you need to be realistic about it, and you can have a plus or minus 0.1 reliability index. So what am I going to do? I'm going to run about 10 simulations in this one. Okay, and I'll set up a table here, 10 simulations, and in each simulation I'm going to put in 10,000 iterations. I'm going to use a Monte Carlo simulation with a random number generator of Mersenne twister. How do I do that? Well, you go up here and you see the settings here. I set up the 10,000 iterations here and 10 simulations here. I can actually go into the settings, and I can set the same numbers here, 10,000 and 10. And I'm going to, if my computer has multiple CPUs, like it has got 8 CPUs, I can enable that function there, and it will run faster. Then I can go into sampling and say I want to use Monte Carlo simulation. You have also the option of using Latin hypercube. Then you're going to choose randomly there, and then what you're going to do is that you are going to go in and say what random number generator I'm going to use. I'm going to use the Mersenne twister, which is as good as any for my purpose there, and then I'm going to say I'm going to run it. Okay, how am I going to run it? I'm going to start my distribution or the simulation here, and what I urge you to watch is what happens to this particular graph here. Okay, and you will see that with each simulation, each one of this graph is updated. So let me open this out, and I'm going to start the simulation. It will take probably a minute or so, so be patient. And I'm going to start that simulation. Look at the right-hand side table which came up. It's going to start in a second. It started the first one. And you see this graphs now changing? That is all the random simulations which are going on there, and I'm on simulation number 10, and then it did it there. and what it's doing, it's writing the data now. And what had happened was that I wrote the data. Let me close this thing out now, and let's look at the results. Okay, what I'm going to do is that I got all of these different simulations where I got different beta value. I'm going to look at the first simulation here, which is 3.09, and what I did was, instead of having that curve here which was overlapping in browse results, I'm now going to fit in an actual curve to that one there. And how did I do that thing? Well, here is how I'm going to do it. For example, if it is resistance, I'm going to browse the results. I can go into distribution fitting. I can fit a curve and see what happened. I figured out it's log normal, so log normal is the first one there. I can take that log normal function, the one which was fitted, the smooth line, I can write it to a cell, okay? And what cell am I going to write it to? Here is what I'm going to do. I'm going to write it to this particular cell of resistance and say, okay. So what it did, it now brought in all of the formulas in here, the mean value, the standard deviation, the risk shift and things like that. And I can do the same thing for the load also. And now once I do it here, the smooth curve, I can go into define distributions and look what I have. Smooth curves, textbook style, like what I was showing in the presentation. So now let me zoom in on this one here and let's play around with this a little bit. You see this overlap zone in here? Let's try to zoom in on this one, okay? And let me do one thing. Let me just move this somewhere here. I'm going to zoom in on this one. And look at this overlap zone here. You see this overlap zone? Does it look like anything, the eye candy which I showed you, which was perfectly symmetrical? Well, it was perfectly symmetrical because I had normal distributions. But in reality, it can be anything there, and you can have this overlap zone here. Now, the interesting thing about the overlap zone is that you can now see this two tabs at the top, that the blue is the one for the resistance curve, the red is for the load curve. Now, let me move this tab here. If I go to the center of this one here, it's 5.53. Let me try to adjust it there. I'm going to try to put a 5.49. It's almost right on the intersection point. Here is something interesting. What you are finding out that for the red curve here, there's 0.1% chance that your load would be greater than the resistance. While for the blue curve here, you see that 0.7% of the curve is still on the left-hand side of the intersection. So there is a 0.1 probability that your load would be greater than the resistance. There's a 0.7% probability that your resistance would be less than the load. But what does it actually mean in terms of reliability index? I have to calculate the area of that overlap. What do I do for the area of the overlap? What did I tell you? I need to convert it into one-tailed representation. So how am I going to do that? Okay, here is how I'm going to do that. Remember this function G equal to R minus QT? I did that function in here, okay, which was the resistance minus load. I can browse the results, and this is how the resistance minus the load looks like. Okay, now I come in here and say, okay, I'm going to fit in a function. I'll fit in a function. I get a certain function in here, and what I'm going to do is that I'm going to write this function to this particular cell here, okay, G equal to R minus Q, and I'm going to look at the distribution here. Look at that, something very neat happened here. I've converted it into single tail distribution, and the area of the curve to the left-hand side of 0, you see this one here, is the probability of failure. And let me zoom in on it. I zoom in on that one there, and I can see, okay, now this is pretty much textbook style. If I were to measure the area under the curve, that's 0.1%, okay, and if I'm 0.1%, then what is the probability of failure there? Well, actually 0.1% happened to be 0.000099, which is 0.099% of failure, which is 1 in 1,000 approximately. 1 in 1,000 is what? Let me go to this reference. 1 in 1,000 is approximately 3.09. That's what I get here. How did I get that one there? I used the Excel formula 1 minus sine V to get that reliability index. Now that met my criteria that I'm greater than 3.00 and therefore I'm okay. You see, now it's already been an hour in this presentation and I can keep going on and on and on and things like that, but there's no point to it. I mean, where does it end? I can go on for 2 days on this one, but I've achieved the goal of this presentation where I showed you on how at-risk can be used for doing LRFD calibration. So let me go back to my presentation here. And what I told you is that I used a pre-programmed spreadsheet with certain known uncertainties and things like that. I used a particular system. And what really came about in this particular presentation that I discussed the concept of LRFD, and what I demonstrated to you that the at-risk program can be very useful in calibration of load and resistance factors using Monte Carlo simulation. You can use Latin hypercube also. The beauty is that you can have many different probability density functions. You can perform parametric analysis, and when you look at the graphics, you get a much better feel of what you are doing. Because if you don't have those kind of graphics, you are always imagining things on how it might be. So that really brings me to a closure on this one here. I'm going to give you certain references here. What I noted up at the top, this is a very limited set of references. It's indexed to civil engineering features and AASHTO, so I've given you some references there. And then, of course, the Palisade thing, like Jameson mentioned right at the top there, you can have, what did you call Jameson, the demonstration version. You can freely download it and play around with it. And
yes, the trial version.
Yeah, that's right, and a couple of articles which I've written which might be useful to you, and of course with the availability of Google and Bing and things like that, you will find nice PDF distributions of several different ones there, so that's what I used. And that really brings me to the end of this presentation. It's about an hour, I believe, Jameson. So what I'm going to do, what do I do here? Are there any questions?
We could leave your slide up there for a minute, and thank you so much, Naresh, because that was a really excellent explanation of this concept. And I'm so glad we recorded this, because this is going to be an excellent resource about this. We have, if okay on your side, we have time to take a question or two. You can type in a question in the chat panel. If we don't have any questions, I'll be sending out a email with everybody's contact information, and you can certainly email Naresh a question or me a question.
And my email address is noted on the slide. So you can send it here, or you can send it to Jameson and he can forward it to me.
Great. I think, Naresh, see on your side, if you in the Q&A panel, we might have one question there. I'm not sure.
How do I get to the Q&A? I seem to have lost it. I'm sharing my desktop. I seem to have lost the ability of.
Oh, okay. I'll let me grab the. Let me see if I can.
Okay. Now I see it there. There's a question which says, "Good presentation. Can we have a copy of the PowerPoint?" What I'll do is that I made a PDF of the presentation, but I'm trying to read this name, Zanikesh. Pardon me if I'm not reading it correctly. You've got something better than a copy of the presentation, because this whole thing was recorded live and it's going to be on the Palisade website, correct, Jameson?
Yes, that's correct.
Yeah, so you've got something better than a PowerPoint here. You have my whole PowerPoint presentation, including my commentary on it. So I think that would be even better than the PDF version of the PowerPoint. But certainly you got my email address on there, Zanikesh. Please send me an email and I'll be happy to send you a PDF copy of the presentation.
Great. And yes, I'll be sending a link out to the recording to everybody who is here, and also everybody who signed up who wasn't able to make it. If you're watching this recording sometime later, and if you have any questions, please let us know about that. Well, if there's no more questions, Naresh, I should let you go, and we really appreciate this. This was excellent.
Thank you very much. Good luck, everybody.
Yes, good luck, everybody, and thank you.
Thanks. Bye.
Bye.